As for the 7.5 homework, the last couple of questions were about a statistics connection, and we didn't do that example in the notes. We kind of look back in and gave you what that probability function is, and then we could finite that after we plug in some values. We are not going to go over those. I'm sure there are probably questions on them, but we're not going to go over those questions. We're going to focus on the details of what's going to be on your test tomorrow. Use our time for review.
We can assume that won't be on the test.
Yeah, it's one of those things again that like they say you should have seen, but I've never actually seen it show up on an AP exam. Whereas Newton's law of cooling, which they say you should see, I have seen show up.
Do you mind if I borrow the scissors?
Go ahead. So on your test, there is no take home. There is a calculator portion and a no calculator portion. The calculator portion has 7 multiple choice. The non-calculator portion has 2 multiple choice and 1 free response. So that means we're looking at 18 points. That is the problem of the length of our class periods is like when I add up the number of minutes that you're supposed to be allotted for a multiple choice, the number of minutes you're supposed to be allotted for a free response, it just doesn't give a lot of time for a lot of questions. So then every problem individually carries a lot of weight that way. But that's just how much we can fit into one day. So, big topics. In section 1, the big idea is that an integral gives a change in something. So when we integrate a velocity function, it gives us the change in position. Okay, it doesn't just give us a position, it gives us a change in position. So we always need to account for an initial value. Okay. We also learned in that section that when given a rate, like a velocity, and want a what I call a physical amount. So like a distance, we do what? Integrate. Okay. So given velocity, want a distance, we integrate. One of our examples in the notes was given a rate of potato consumption. How many potatoes did we eat? We integrate. Okay, so when you have a rate function and you want to get back to the physical descriptor of how much we actually ate, how far we went, that kind of thing, we integrate. So when I read through a question, if I see the word rate in there, I circle it, I underline it, I do something to remind myself that this is a rate. And then as I keep reading, if I see that I want to know the physical amount of something, I know I'm supposed to integrate that. Okay, so I look for those key words as I read through questions and kind of make notes to myself about what I'm given and what I want. So let's say, for example, I'm given a velocity function is 3 cosine of t plus 4. And I'm given that the initial position is 2. And I want to know the position at time 10. Let's make this a little bit more interesting. Position at 1 is 2.
Why would you do that?
Let's make it a little bit more interesting. What do?
Take the integral of velocity.
Take the integral of velocity.
From 1 to 10.
From 1 to 10. Why from 1 to 10?
Because we know what 1 is.
Because we know 1 and we want to know 10. So we want to integrate velocity to get position. We want to put limits of integration on that, and we want a limit that we know and a limit that we want to know. Okay? We could finite that and get something. Okay, so we'll say that is whatever it is when we finite it. Is that my answer?
No.
No, but it will likely be a multiple choice option. Not a promise. Sometimes they're not that mean, usually they are. What do I need to do to turn that into my answer?
Subtract 2.
Add 2 to it. And that will be your final answer. I should put my equals over here. Okay. We had a position of 2 at time 1. The integral tells us how far we went between time 1 and time 10. Okay, a change in position. Now, what if these times were reversed? And so our given was like at time 10, and we were asked about time 1. What would we do then?
Flip it.
Same thing, but we would subtract, or we could flip the integral and go from 10 to 1. Okay? But somehow we need to account for kind of that. We're going back in time here from our given information. So when we would integrate, if I integrate from 1 to 10, that tells me how far it went between 1 and 10. But I know at 10 it was at a 2, so I have to subtract back from that to see where it started. Okay? Well, if I change them. Okay? So somehow we have to account for that initial position. Often drawing a picture, just a sketch, can help you think about whether you would need to add or subtract on that initial position. Okay. All right, so that was section 1. Section 2. Area. How do I find the area between two curves?
Upper minus lower.
Bottom.
Okay, integrate upper minus lower in terms of x from A to B. Either points that you're given, or often we want to find the area enclosed by two curves, so those would be points of intersection. Okay. Sometimes doing upper minus lower is not extremely convenient. So what can we do instead?
Right minus left.
We can integrate right minus left,
Do you love it?
but that will have y's in it. And then we would integrate from C to D, which would be y values. Whatever your limits of integration are, make sure they are the same type of variable as the variable in the problem. That sounds a little bit obvious, but it's a super common mistake because we're so used to always working with x's that even when our problem has y's in it, we will often take the x value of the intersection and put it on there. And again, not a guarantee that would be an answer choice, but it's likely because they are that mean and they know that that's what students do wrong. So we want to make sure that whatever variable is in our integrand, that's the type of variable that we're using for our limits. So we'd be using the y values of the intersection points. Okay. So, example, let's say I want to find the area enclosed by 2x squared and x squared minus 2, or x to the fourth minus 2x squared.
Calculator.
With given picture.
Ah,
Even in the book it says not to scale, and mine's not either. So what do I?
Wait, what is that? -2.8?
Yeah,
Spider-Man.
symmetrical.
Integrate, do 2x squared minus x to the fourth minus 2x squared, and then take the integral of that
From -2 to 2.
-2 to 2.
Okay. So we've got x's in our problem, so we want to choose the x's from the points. We're doing an upper minus a lower. The upper curve is the parabola, the lower curve is the quartic. And common mistake, make sure that you subtract the entire second function. So I have parentheses in here. If this was a by hand problem, you need to make sure you distribute that negative. If it's a calculator problem, you would need to make sure that you either distribute the negative before typing it into finite or put parentheses into your finite. Okay? But we need to make sure that we're subtracting the whole second function. That's a really common mistake. The students will just write the first function minus and then the second function without taking into account that the second function has more than one term. Okay? Questions?
Will these area problems usually be finite or
If
by hand?
If no graph is provided and you're looking for an area between two curves, that would be a calculated question and we would finite it because they're not going to expect you to be able to find the intersection points by hand. Okay? If something was like this where it's given the picture so you don't actually have to use your calculator to find the graphs or the points of intersection, then it would depend on how disgusting the arithmetic is. They really try to not have you do bad arithmetic on the no calculator part. I mean, obviously we have to do some, but same thing with algebra. They want to make sure that they're really testing if you know calculus and not if you know algebra or arithmetic.
Okay.
So it would really boil down to how bad this gets. This one would get pretty bad.
Yeah, you have to do it.
Because we would end up, when we integrate this first thing, we'd have 2/3 x to the third, but then this would be 1/5 x to the fifth, so I'm not going to work thirds and with fifths, and it would end up pretty messy on this one. So they would probably contrive it so that the arithmetic was 9.
Alright.
It's just, if you switched it like on its side, you switched the y's with x's, how would you do that?
That would not be convenient in this one because we don't have a consistent right hand and left hand function. So we could just consider like half of this since it's symmetrical and then double it. So that would be another option, would just be to go from like 0 to 2 and double this. That would give us the same thing because it's completely symmetrical. But as far as right and left, down here we have an issue that the same function is both on the right and on the left. And so we couldn't really do that. Also, we would need to have it solved for x to be able to do that. And when we solve these for x, I'm going to get plus or minus square root of y over 2. And so then we end up with a non-function. So.
Yeah, don't do
Yes.
that.
If you were to keep solving this, like if you were to integrate it or whatever, wouldn't the 2x squared be 4x squared? Because,
Yes.
Okay.
Yeah, you can combine those together and make them work for
And then why is there 2 in the front?
If we decided to go from 0 to 2, then we could just double,
And
since
double.
both parts are the same.
So if you are using the y values in the right and left sides, you're going to want to solve for x.
Yes, if you're using y values, you need y's in the problem. So that means you'll have to solve for the x.
Yeah.
All right. Section 3, volume. For volume, there are 2 types of questions. There are known cross-section, where they will tell you that when you take a slice, it's a particular shape, like a equilateral triangle, a square, a semicircle, but some consistent shape for our slices. Or we have a revolution, and then the cross-sections would be circles or washers. Let's say my function is x squared, and I'm going to go from x being 0 to 3. And my cross section is an equilateral triangle. Okay. So my curve looks something like this. Then within there, we are going to make equilateral triangles at any given point. So our cross section look like this. So our kind of steps in our notes said sketch out the region in the solid, and then draw out your cross section. What is the area of a triangle?
1/2 base times
1/2 base times height.
Or this
What is the base of this triangle?
The
9
y value or the function value.
x squared.
It'd be the function value. So it'd be x squared at any general point.
Yeah.
9 is the biggest one, but down at the origin it really has a base of 0.
Oh, that's right.
So in general, the base of that triangle is going to be whatever the curve happens to be. 1/2 base times height of this triangle. How do we find that?
This is
30,
x.
60, 90.
30, 60, 90 triangle. If it was equilateral, it was 60, 60, 60. So if I cut it down the middle, I end up with some 30, 60, 90s. So in those 30, 60, 90s, each of this side is now going to be split equally to be x squared over 2. And our height would then be
Square root of 3, x squared.
square root of 3, x squared over 2. Okay, the height of a 30, 60, 90 is square root of 3 times the base. So our area is then 1/2 base times height. So it's square root of 3 over 4, x to the 4th. And how do I turn area into volume?
Integrate it.
The derivative.
Integrate. So we're going to integrate from 0 to 3.
Would this be infinite?
No.
It's not
Because
bad
you
at
can just
all.
pull that out front and then it's a
Yeah.
fifth x
But
to the
this is-
fifth.
this is-
So when we integrate, we get a 5th x to the 5th. And I don't know, maybe doing 3 to the 5th is probably more than they would expect you to do. So I
You
get
might have it 3 to the
a
5th.
20th times whatever
Yeah.
3 to the 5th
I
happens
bet-
to
I bet
be.
that's what it would
So that part of the arithmetic is a little bit too gross. They probably would have picked a smaller number, like 2 to the 5th would maybe be something they would say you could probably handle just multiplying 2, 4, 8, 16, 32. 3 to the 5th is a little bit more ambitious. It's 243, I think, but that's a little bit more than I would expect them to make you do.
So when we are finding the base and heights of the geometric shapes, is it always going to be found using like either trig or formulas?
For a triangle, I mean, if they said it's a right triangle, so they could say something like right isosceles triangle. Okay, so then the base and the height would be the same thing. So it'd just be the curve for both of them in that case. It's really just an equilateral where you're going to end up running into needing trig.
Okay, what about
Only?
like if you're trying to find the height of the trapezoid or something? Would you have?
We don't usually use trapezoids in this. Back in our trapezoidal rule and like area approximations and stuff, then we did, but I can't say I've ever really seen a trapezoid come into a volume question. A square would, but then again, base and height would both just be the curve. Yeah.
How do you find the height again?
I find the height again. 30, 60, 90 triangle.
Yep.
So that base is going to be cut equally to be x squared over 2. And the height of a 30, 60, 90 across from the 60 is square root of 3 times the base.
How do you get the triangle from the graph? Just draw the line
On the x-axis.
Yeah, so the base is perpendicular to the x-axis, and then we would draw up just so that it's approximately equilateral.
Is that supposed to be an approximation? Is that like is that supposed to like work
What?
for guessing the area?
For guessing?
For approximating the area?
I don't know why we're approximating anything.
This is
That's
exact
area.
or volume. This is exact volume.
It's the exact volume.
With
It's not an approximation. It's an exact volume.
Is that straight line perpendicular to x?
Yes. Yep, we're drawing our triangles perpendicular to.
That triangle would
Yeah.
look like
common.
Oh, you're right. Yeah.
It would look like
That
this.
triangle looks like that way. I mean, that can be
I was thinking that was like actually what we were doing.
Guys, quiet down.
have the two sides and the opposite side.
Guys, quiet. The problems almost always, in fact, they will always say that your cross-section is going to be perpendicular to one of your axes. So either your x-axis or your y-axis. So that the base will be perpendicular to either your x-axis or your y-axis. If they're perpendicular to y-axis, then we'd be working with y's in the problem. But it will always be either be drawn perpendicular to the x-axis or perpendicular to y-axis. Let's do a revolution problem. Let's say that we're going to do y equals x squared again. We'll go 0 to 3 again. So I'm not feeling creative. And we're going to revolve that around the line of x equals negative 1. Okay, so it's like a bowl with no bottom. Like it's completely separate. The two pieces don't come together. So it's a very strange shape. It's hollow in the bottom.
It's got extremely
It's
sharp
got
points.
straight sides on the outside, so it's like a cylinder on the outside. On the inside, it rounds down, but it's actually missing the bottom, so it wouldn't actually contain anything.
It's
If it was sitting on the ground, it would.
If it was sitting on the ground, it would contain something, not liquid, but all right. So
it wouldn't even be a one piece.
first step, it would be one piece.
Oh, well, you're right.
First step
He's got the dome around it.
is draw the solid. Okay, it doesn't have to be great, just a sketch so you can kind of think about what this thing looks like. Then second step is draw our cross section. When we're doing a revolution, our cross sections are going to be circles or washers of some kind. Those circles are stacking up along the y-axis. So that means we are going to want to have this problem solved for x, so we have y's in our problem. You could also do this problem with shells if you prefer. Most people don't.
We just neglect the plus or minus.
Yes, because we're only dealing with a section that's in the first quadrant. So that would just be the positive portion. The other part is reflecting over, but that's not actually part of the shape that we revolved. So what we revolved was only the positive portion.
Why do you want to solve for x?
Because our circles are stacking up along our y-axis. So we're going to want y's in our problem. So with a washer, we care about our inner radius and our outer radius. What is the inner radius?
X squared.
Formula square root of r squared.
By r.
R squared.
Okay, so our area is going to be pi big radius squared minus little radius squared. Area of the big circle minus the little circle. But what is our little radius going to be?
X squared.
Close. It'll have something to do with the
Minus
curve.
Yeah. X squared plus 1.
Okay, so we're going to need to add 1 to whatever the curve is, because the curve would take us from our axis out to the line, but our center of our revolution is 1 more unit away from that. So our big radius is going to be our curve, but we're working with square root of y, not x squared, plus 1
Is that always true?
Always.
is what always true.
The radius, the little radius is always.
Oh, sorry, that's our little radius.
Yeah, the little radius is always one away from the big radius.
No, that's just because of where I revolved it
Yeah.
around.
It's 1,000 away.
So how do you know that?
Because
Asymptote.
going from the axis to the curve gives us part of our radius, and the rest of our radius is one more unit away from the axis.
So you're measuring from the axis, not from the asymptote?
Well, it's not asymptote, it's our revolution line. It's the center of the figure. So we're measuring from the center of the figure, and the center of the figure is always one away from the axis, and then the axis is some distance away from the curve.
Okay.
Why would it be square root of y instead of, because I thought it was x squared plus 1 for the small radius.
You don't want to do it.
We don't want to do it with x's, because we're stacking our circles up on our y-axis. So we're using the curve, but we're using the x equals version of it, so that y's are going to be in our problem.
Oh, okay.
Same thing, just the other variables in there.
For revolutions,
Yeah.
were you always going to want to solve for x?
It's
Always going to be 16.
Just depends which way your circles are stacking up. So since our circles are stacking upward on this problem, we want y's. If our circles were stacking sideways, like if we revolve around the x-axis,
Oh, okay.
then we would want x's in the problem. Typically, if you're revolving around your x-axis or some other horizontal line, you're going to have x's in there. If you're revolving around a vertical line, you're going to want y's in it, because then the circles stack up.
Will you always get a revolution center point?
Yes. Yeah, the revolution always has a center that is the line of revolution.
What if some portion of it goes down underneath y-axis?
So like if we had a different curve and it went down under the y-axis, it would still, under the x-axis you mean?
Yeah.
It'd be the same.
Both above and
Yeah, it'd be the same thing.
Like,
What is our big radius?
The same
is that just
thing.
'cause you got
Square.
you choose
2 times the same thing.
Why?
What is our big radius?
it's constant.
It's constant.
4.
It's 4. Okay? We're going out to 3 on our x-axis always. Remember the sides of this thing? It's like a cylinder. The sides are not at all curvy. The sides are straight up and down going out to 3. But that 3 is 1 unit away from where we're actually turning this thing around. So it's a distance of 4 from our center on out to that line. So our big radius is 4.
Really horrible fonts.
And to turn this area into volume, we're going to finint it from x is 0 to x is 3. Oh, sorry, not x is 0 to x is 3. From y is 0 to y is 9. See, I did the common student mistake there. So used to always thinking about x's, but in this problem, since we're stacking our circles and we've got y's in the problem, we need to make sure we have y's in our limits. Yeah.
How do we know it's up to 9?
Because x goes out to 3, and our equation is y equals x squared. Yes.
If you, this is an algebra question, I feel kind of stupid asking.
No, ask
If
away.
you have 9x squared, and you take the square root of that full thing, is that 3x?
Yes.
Okay. So
Yeah,
you
take the square root of both
You
parts.
take the square root of x squared and then take the square root of 9.
You can do that for a product, not for a sum. So if you had 9 plus x squared, you can't just take the square root of each part of the sum, but you can for a product.
Square root of parentheses
Yeah.
9.
Would that
Why
be
couldn't
plus
you do
or
that for
minus
some?
3 times plus or minus x?
Oh, because it's factor.
I don't know. I don't want to think about it.
Section.
Section 4 is length.
Improve it.
Length is the integral from a to b, square root of 1 plus derivative squared dx. Or you could do it dy, and that would be fine as well. Just whatever way they give you the equation, go with it. You need one letter alone, but it doesn't matter which letter.
That's dy over dx.
Yep.
Okay.
So remember that this formula comes from our Pythagorean theorem. So that's why we have this square root of stuff squared thing. It's a Pythagorean theorem, and a squared plus b squared equals c squared, and we're adding up lots and lots and lots and lots and lots and lots, infinitely many, really, of those little right triangles to find the length of the curve. So let's say my curve is 2 sine of 4x. Then dy dx is equal to
8 sine, no, 8, negative 8 cosine, no, 8 cosine x.
8 cosine.
Oh, 8 cosine 4x.
You got it.
all right, so the derivative of sine is cosine, and we leave the inside alone, but we need to then multiply by it. That's our chain rule, so we got to multiply by that 4 under the outside when we take our derivative. So then length is square root 1 plus this thing squared, so that'd be 64 cosine squared of 4x dx, and then I don't know, we'll just say 0 to pi. Finint.
No kidding.
Finint.
I can do that.
Use.
Length questions are usually either just a finint question or a which of the following would find the length of, and then this would be like choice, C, and there would be 4 other wrong setups. But usually these problems are too disgusting to be able to algebraically and analytically do. So it will either show up on the calculator part and you finint it, or on the non-calculator part, it will usually just be that it's the setup and not actually the evaluation. John?
If there's like an x squared on the inside of the sign, I'm just trying to remember my chain rule. Does that turn into a 2x on the outside?
Yes.
Okay.
2x on the outside?
If it's an x squared on the
There's an
inside,
x squared.
there would be a 2x on the outside. Like when you do your chain rule.
And that would still be x squared though.
It'd still be an x squared on the inside, but then times a 2x.
I was just trying to remember how my chain rule worked.
Yep. Yes.
So with the square root of that would be 1 plus 8
No.
cosine 4x.
You can't take a square root of a sum. You can't do square roots of the parts. You can see it
Yeah, that's what
if we just do numbers like 9 plus 16.
Peter finit it.
That would be 25, so square root would be 5. But if I just take the square roots of their stuff, I get 7. So it doesn't really work. All right.
Square roots is so
Section 5 that we did last night was just some application questions. Again, really, there isn't too much of that. It all kind of boils back to Section 1 and the big idea that if you are given a rate function and you want an amount, you integrate. All right?
Can you just do one for kicks and giggles?
I don't even have an example that I would like
Make
to
up an
do
example.
of that.
Make up one.
Oh, yeah, because that'll turn out nice. Yeah.
Just do it anyway.
Is there anything with like the newtons or joules or anything?
Or kicks and
Or is that
giggles.
kind of
No, they would give you what you would need to know
Oh, okay.
in terms of
Did we do
physics
that?
formulas. They don't want students who are currently also enrolled in AP Physics to have an advantage over calculus students. So any physics that we needed would be given.
That and 7-1.
Yeah, I think we did like Hooke's law in 7-1 where we talked about a spring and stuff like that, I think. They would give you what you needed.
Okay.
You're not expected to have those formulas memorized.
Can you do a shell example of the volts?
I can.
Joules,
I don't
Remember, it will never be necessary.
joules
Yeah.
are in newtons, right?
I have a question.
Joules are Newton meters.
Okay.
Newtons are
Yeah.
Is shells always
pretty much a
2 pi
weight
x
over
times
GM
the height?
right here,
No.
over second squared.
It's not always x
Per meter per
I'll do a shells example. First, I want to give you your review assignment.
Yeah.
Okay.
I'm all about the review assignment.
Page 413. And I'll give you a list of calculator and a list of no calculator here.
Wait, is this extra credit?
He said he tried
Yes.
going up.
Additional credit.
Yeah, it's an extra grade.
Oh.
It's not like out of 0, it's out of a grade, but it's an extra grade.
But hey, you know what?
But they are strategically picked. So,
You watch, Sean.
Usually I don't have enough time.
I love all of these calculator questions.
I have all day.
there is one question in here that's about Hooke's Law. So just, feel free to look up Hooke's Law when you're doing that. Again, I don't expect that you would need to have Hooke's Law memorized at all. You don't for this test, and I wouldn't expect that on the actual AP. And then, again, it's not required for tomorrow, but doing your journal question would be a good way to practice an area and volume problem. And then I had a request for a shell. If you don't want to listen, that's fine, but please be quiet so that if other people do want to listen, they can. I'm going to do the same one, actually, that we already did. So we took the curve y equals x squared, and we revolved it around the line of x equals -1. Okay, so we did it with washers before. We could also do this with shells. And when we cut a shell, I would be cutting some like little very, very thin tree ring out of this thing. Okay? They would be starting right at the edge here and then going all the way out to the biggest possible tree ring. Okay? When I have a tree ring, I can then slice vertically down that ring and unroll it, and it will become a rectangle. Area of a rectangle is length times width. The length of this will have been the circumference of our ring, which is 2 pi r. The height of this will have been the curve. Our radius of any of these shells is going to go from our line of revolution out to wherever we cut that ring.
What is, let's say for height, for like
Curve.
curve?
For the height.
Yes.
So then, when we're doing these shells, we're going to work the problem with x's. Okay? So when you do a shell, you're working the problem with the variable that would be the opposite of if you were doing stacked circles or washers. So we're going to do our problem with x's. So what is the length of one of these radii in terms of x?
X plus 1.
Okay, so we've got always a distance of 1 here, but then as we move over, we're adding to it some x value on up to an x value of 3. So our radius is going to be x plus 1. So that answers your question about is the radius always x?
Nope.
Not if we're revolving around a line other than an axis. If we're revolving around the axis, yes, but around a line other than an axis, no.
It's not x squared plus 1?
No, it's just a horizontal length of x away from the line. The curve defines the height, so our curve is going to be the x squared for the height. So then the area of this is going to be 2 pi x plus 1 times x squared. And to turn area into volume, we're going to integrate. We've got x's in our problem, so we want x's as our limits, 0 to 3.
But you won't ever have to do that, right?
You won't ever have to do shells, but there would be problems like this where it could go one way or the other. So you can either think about washers and have to solve for the other letter, or you can think about shells and be able to use the formula the way it is. And it's a preference thing. There will never be a problem for which shells is necessary. Okay?
It's such a problem.